Hello, this is the fourth week of your modelling project, and during this week you'll be writing up your report and sending it to your tutor. We didn't feel there was much help we could give you with your modelling at this late stage. So what we're going to do in this television programme is talk about the exam. We'll be using this specimen exam paper to give you some hints and tips about how to revise and about how to tackle the exam. And we'll show you how the handbook can help you with the questions when you're actually sitting in the exam room. Now we'll be looking at 4 questions, but we won't be looking at the answers in any detail, because you've got them here in the specimen solutions. Instead, we'll be concentrating on ideas for revision and on the exam techniques that will help you on the actual day. Let's imagine you've just sat down in the exam room and taken a first look at the exam paper. Naturally, you're feeling nervous. So what do? Anne?
Everyone develops their own way of dealing with nervousness in exams. One way is to first find a couple of straightforward questions which you can do and answer those. Well, in part 1 you have to do 8 out of the 10 questions anyway, so picking a couple of them won't mean that you're going to do any unnecessary work. And there are certain topics which are bound to be asked. For example, there's always going to be a question on differential equations. Also in part 1, questions are always short, so this is a good place to look for questions to settle you into the exam. It's often a good idea at the beginning to avoid numerical questions, which would involve a keying sequence on your calculator. A nervous finger may well press the wrong button. So here's the exam paper. Let's look at part 1 and see which questions we might tackle first. Now question 2 is just what I'm looking for. Here's a copy of it. It asks me to solve a differential equation. Here's the equation. It's x dy dx equals 4x squared minus 2y. And I have to decide how to solve it. So what method can we use? Well, remember that you have the handbook with you in the exam. Here it is. And it's worth getting to know how to use it and where everything is. Now, the unit summaries start on page 19 of the handbook, and they're useful for reminding you of procedures, and that's the case here. Here, we've got a first-order differential equation, and they are in Unit 2. So we can look them up in the Unit 2 summary, which is on page 20. Here's a copy of the entry, and the exact methods all refer to equations of the form dy dx equals something. So let's get our equation in that form. Our equation, when divided by x, gives dy dx equals 4x minus 2 over x y. Now, looking in the handbook again, we see that this is the kind of equation that can be solved using the integrating factor method. The handbook says that if the differential equation is in this form, the integrating factor is this. So, for our equation, L of x is minus 2 over x. That means I can go on to write the integrating factor p of x is equal to the exponential of the integral of, now the 2 minuses will go together to make 2 over x dx. And now doing the integration, I've got the exponential of twice log to the base e of x. This 2 comes inside the log to make x squared, so it's exponential of log to the base e of x squared. Log and exp are inverse functions, so that's just x squared. The next step is to multiply both sides of this equation by the integrating factor x squared.
You've got the details of the actual working in your solutions to the specimen exam paper. So we'll come back to Anne after she's completed the question.
Finally, I'll substitute in for c, and at the same time I'm going to divide through by x squared, so I get y equals x squared minus 1 over x squared. Now it's a good idea to check the result, provided it doesn't take too long, and especially this one as it's the first question we've tackled. Here it can be done by differentiating this and substituting it into our original equation. So if I differentiate, I get dy dx equals 2x plus 2 over x cubed. In the equation I've got x dy dx, so if I multiply this by x, then I'm going to get 2x squared plus 2 over x squared. Now the right-hand side of the equation was 4x squared minus 2y. Substituting in then, I've got 4x squared minus 2x squared plus 2 over x squared. And you can see that if I combine these x squared terms, I get the same expression as I have here. So now we've done one question, and by now you'll be beginning to settle down. There are two general points arising from all of this. First, always check your answer if there's a nice, straightforward way of doing so. And secondly, don't forget to use your handbook. Now, what about another question from part 1? Mike?
Now that question was on methods. Let's now look at one of the short questions on mathematical models. In part 1, there are 5 short questions on modelling. On the specimen paper, of those there are 3 short questions on mechanical models and 2 on non-mechanical models. Also in part 3, there are 3 long questions on mechanics and just 1 on non-mechanical models. In the actual paper, there will be a similar balance of questions between these 2 parts of the course. I've chosen to look at question 10. This is a question on heat transfer through a wall. Now, as Anne was saying, you should make full use of the handbook during the exam. That means you need to know where you can find things in the handbook. And you also need to know what's in it and what isn't. Now, heat transfer is in Unit 12. So we can look at the summary of Unit 12 in the handbook. Now, if you're not sure which unit you need, you can use the index at the back. Here we might look up U value. Here it is. And it refers us to the summary of Unit 12. Now, in question 10, we'd like to use the formula for the U value of a wall. But unfortunately, that particular formula isn't in the handbook. Here's the relevant paragraph. But don't forget that you can annotate the handbook as you want, and you might decide that's one formula to write in here, as I've done. It's this one. Now this question gives the values of the constants in the formula for U. Here they are. So all we have to do is to put those values into the formula and press the right buttons on the calculator. So let's do that. Well, the convective heat transfer coefficient inside, that's 10. The thickness of the wall, 0.2 of a metre. Thermal conductivity, 0.7. And H out, 20. So let's get the calculator. .2 divided by 0.7 plus 1 over 20. Finally take the inverse. To 4 figures, it's 2.295. And the units, So there we are, the U value is 2.295. Now, this question also asks for the total rate of heat transfer. And that formula is in the handbook. Here it is. We've already found U, and the values for A and the two temperatures, they're given in the question. A, that's 15 square meters. The inside temperature is 20, and the outside temperature is 10 degrees centigrade. So we can now calculate Q and finish off the question.
Now, before you go into the exam, it's a good idea to know what to expect. In other words, to know the structure of the exam paper and the number of questions you have to answer in each part. The structure of the actual exam paper is exactly the same as it is in the specimen exam paper. There are 3 parts to it. As we've already discussed, the first part contains short questions. There are 10 of these, 5 on methods and 5 on modelling, and you have to do 8 of them. Parts 2 and 3 both contain longer questions, and there's more choice. Part 2 is on methods and contains 4 questions, and you're asked to tackle 2 of them. Part 3 is on modelling, and again you have to answer 2 out of 4. What about marks for each part? Well, Part 1 carries 40% of the marks, whilst Parts 2 and 3 carry 30% each. So that's the structure of the paper, but how long should you spend on each part?
Well, the bulk of the easy marks can be gained by answering 8 questions in Part 1. And as Anne said, that's worth 40% of the total mark. So you should think in terms of spending 40% of your time on Part 1. That's just a bit over an hour. But what about the longer questions? Well, you only have to answer 2 questions in Part 2 and 2 in Part 3. Each question is worth 15% of the total mark, which means you should think about spending 25 to 30 minutes on each question, just a bit under half an hour. You shouldn't spend much more than that on just one question. So keep your eye on the clock. So let's have a look at how to answer questions from Parts 2 and 3.
For the first longer question, let's look at Part 2. I've chosen question 12, which is about a differential equation. Now, the first thing to do, especially in longer questions, is to read the question carefully. Make sure you understand exactly what's being asked for. Before, in question 2, we were asked to solve a differential equation analytically, but here we're asked to solve a differential equation by a numerical method. We're told to use the predictor-corrector method, or Euler trapezoidal method, with a particular step size to find y at a given value of x. So, once again, let's turn to the handbook. We can find the Euler trapezoidal method in the unit summary for Unit 19, and that's on page 37. Here's the method. You have to interpret the handbook entry and set up the method for the given differential equation. But there's a problem here because the handbook entry has a misprint in it. It's here, in the second line of equations. This xr should be xr plus 1. You may have corrected it already, but if not, do it after the programme. And it might be an idea to check the stop presses for any other misprints at the same time. Now for question 12. Y dashed m of xy is 1 minus x squared y. And here I've interpreted the handbook entry for this differential equation. And we have to start off with x naught is 0, y naught is 1, and h is 0.1. That means to get to x is 0.2, I'm going to have to do 2 cycles of the method. And here at the end is y2, it's 1.1965036. Now, y2 is an approximate solution of y at x equals 0.2. And in part 2 of this question, you're given the correct value to 5 decimal places. So you can use it to check that your value of y2 is a reasonable figure. Of course, you wouldn't expect it to be correct to 5 decimal places, but it shouldn't be too different. And it isn't. In this case, they're the same to 4 significant figures. So I can be pretty confident that the calculation is okay so far. Now for the rest of the question. Part 2 first. The question asks us to find the step length needed to give an accuracy of 6 decimal places for the approximation to y at 0.2. In other words, to find a value of h. Now this time, the handbook's not quite so helpful, but your experience during the course should guide you. The handbook says that the local truncation error for the method is proportional to h cubed. And this means that the global error is proportional to h squared. So we can write y2 minus y at 0.2 is equal to some constant c times h squared. From the calculations in part 1 with h equals 0.1, we can find c. And then we can use this formula to find the value of h, which will give us the required accuracy. For the last part of the question, we need the condition for absolute stability. And again, we could use the handbook to help us do the question. Here's the relevant entry. The condition is that this is in the interval of absolute stability for the Euler trapezoidal method. The next entry in the handbook tells us that this is the interval -2, 0. You can find the details of how to do the question in the specimen solutions. Now, this question showed that one way of checking your answer is to use the information in the question. So, when is it worth checking, and how? Well, there are 3 tips I can give you. Firstly, if a check is easy, then it's worth doing, as it was here. Secondly, never leave the exam room until your 3 hours are up. If you've done the right number of questions and there's still time left, then spend it going back and checking through what you've done. And thirdly, try to use a different method to do your checking if you can. That way, you avoid making the same mistake twice. Of course, there's no point if the new method is very complicated, because it might take a long time and you could make a mistake using it. But sometimes you can use the answer itself as a check, as for instance I did in question 2.
Right, so let's take a look at one of the questions in part 3. Let's look at question 17. This is a question on the normal mode motion of a system consisting of particles and springs. There will almost certainly be a question on oscillations, either simple harmonic motion, damped vibrations, or normal modes, as we've got here. And don't forget that Newton's law of motion gives a differential equation, so it's particularly important that you master the techniques for solving differential equations. The system here has 2 particles and 3 springs. The 3 springs each have natural length L0, and the total distance from A to D is 3L0. So in equilibrium, each of the 3 springs will have its natural length. Well, I've got the diagram here. Let's mark on the displacements of the 2 particles. They're x1 and x2 to the right. Now the first thing we need are the extensions of the 3 springs. Let's first look at the spring AB. All right, the particle B moves a distance x1 to the right, so that means that the spring AB is extended by x1. What about BC? Well, C moves by a distance x2 to the right, so that extends the spring by a distance x2, but on the other hand, B also moves by a distance x1 to the right, which contracts the spring by a distance x1. So the overall extension of the spring BC is x2 minus x1. Finally, CD. Well, C moves by a distance x2 to the right, so the spring CD is contracted by a distance x2. In other words, CD is extended by minus x2. We can now look at the tensions, so let's mark them onto the diagram. We'll call them T1, T2 and T3. And the tensions, they're just the stiffness times the extension. So the tension in the spring AB is K times its extension. In BC, that'll be K times x2 minus x1. And finally, CD, that its tension will be K times its extension, which is minus x2. And now we've found the tensions, we can find the equations of motion. Firstly, the equation of motion for the particle B. Mass times acceleration equals the total force. The forces acting on B are T2 to the right and T1 to the left. So the total force is T2 minus T1. Similarly for particle C. Mass times acceleration is the total force, T3 to the right, T2 to the left, so the total force is T3 minus T2. And so now we can substitute the tensions into the equations of motion. And you should get the differential equations which are given in the question. Notice that the question itself gives you the equations of motion. So even if you can't do the first part, you can still go on and complete the rest of the question. And notice too that the wording of the question helps you by suggesting the strategy for solving it. In the first part, we're asked to find the equations of motion. And then in the second part, we use those to find the normal mode motions. In the third part, we're asked to write down expressions for the general displacements of the particles. They're just linear combinations of the normal mode motions. One more hint. When you finish the solution, it's a good idea to read through the question again. For example, part 2 of question 17 asks you for the normal mode motions, but it also asks you to describe the normal mode motions in words. You might easily forget to do that.
We've concentrated mostly on what to do in the exam room, but let's finish by giving you a few suggestions about revision. Firstly, if you need some extra problems to practice on, then there are a lot of these in the summer school material.
And to remind yourself about what's in the course, read the summaries at the end of each section of each unit.
But don't restrict yourself to just reading the summaries or the units. It's very important that you practice doing problems.
And practice doing an exam paper. Set aside 3 hours and have a go at the specimen exam paper under exam conditions.
And if you do get stuck at all in your revision, don't hesitate to get in touch with your tutor.
Well, all we can say now is good luck. We are sure that as you've got this far in the course, you'll be okay.